Bias in machine learning is a problem that's been known for some time now and is becoming increasingly important to address as we use these sorts of automated decision systems to make or help us make decisions in increasingly significant and sensitive areas that have the potential to impact people's lives greatly. These domains include hiring, criminal justice, and healthcare, to name a few. A perfect example of this sort of problem was uncovered a few years ago by ProPublica, where they essentially demonstrated that a system that was already deployed by the United States to try and help predict likelihood of criminal recidivism was racially biased. Now, obviously, it's to our benefit in the short term to combat these problems, to try and ensure that the decisions that are being made are in fact fair, whether they be in employment, in the criminal justice system, or in the dissemination of healthcare. However, these problems are also worth addressing for long-term benefits, in that we want to prevent the reinforcement of these sort of systems-level biases, not only within the machine learning algorithms and these systems themselves, but also within human actors who often work under the assumption that an automated system like this, a computer, a machine, what have you, is by its very nature an impartial, unbiased third party. We in this community, and we hope a growing proportion of the general public, realize that this is a deeply flawed assumption. There's plenty of current news articles on bias in machine learning, and in response to both these news articles and the actual problems themselves, many companies are beginning to focus on bias and explainability. A lot of the solutions that are being proposed are technical in nature. In other words, encoding fairness in some fashion within these systems and within these tools. But what does that exactly look like? Well, many fairness definitions are developed by machine learning experts. In other words, mathematicians and computer scientists using lots of math and technical concepts such as statistical parity, accuracy under error rates, and causality. However, these systems, or the systems that employ these definitions, are largely used by and impact non-machine learning experts in a diverse array of settings, including, as we talked about, hiring, education, criminal justice, and healthcare. So this leads to the question of how we can decide which definitions are appropriate in different real-world settings, if any are indeed appropriate at all. But in order to answer this question, we have to take a step back and answer a different question, which is where our work lies. We ask, does the general public understand mathematical definitions of machine learning fairness and their behavior in real-world settings? Now, I say the general public. You might wonder why we focus on non-experts. The aim of our work is to understand how people who will be impacted by machine learning decisions perceive these fairness definitions. Now, obviously, experts themselves will also be impacted by these systems, but the fact remains that by and large, the vast majority of people who will be impacted and even use these systems are non-experts. They're not computer scientists, they're not machine learning experts, they're not mathematicians. And it's important to get the consideration and the viewpoints of all stakeholders involved in making these decisions, rather than just the narrow viewpoints of the designers who are creating and engineering these systems. So we've formulated a series of research questions to address. First being, can we actually develop a metric to measure lay understanding of machine learning fairness definitions? From there, we move on to address the question of how or if a non-expert audience comprehends machine learning fairness definitions and their implications. And we approach this in through two particular angles. The first being what factors play a role in comprehension, and the second being how or if comprehension and sentiment towards these fairness definitions are related. We address these research questions using an online survey, which asks participants about real-world decision-making scenario and how these decisions can be made fairly. We assess 4 machine learning fairness definitions in our survey. Obviously, this is not all fairness definitions, but we focus on these 4. These are demographic parity, equal opportunity, looking at both false positive rates and false negative rates, and equalized odds. For the clarification of our audience, I'll go through each of these definitions very briefly. Demographic parity is simply the notion that given some sensitive attribute, the likelihood of receiving any particular outcome Y is equal across all groups within that sensitive attribute. So in our survey, we focused on a hiring scenario. So in the purposes of hiring, say your sensitive attribute is gender. Application of demographic parity could be that the proportion of female applicants who receive job offers should equal the proportion of male applicants who receive job offers. Equal opportunity focusing on false positive rates is simply the notion that the false positive rate must be equal across all groups within the sensitive attribute. And analogously, equal opportunity focusing on false negative rates simply is the notion that false negative rates must be equal across all groups within the sensitive attribute. And finally, equalized odds is simply a combination of equal opportunity false positive rates and false negative rates. In the survey itself, participants are presented with the decision-making scenario along with a rule to ensure that the decisions are made fairly. Now, in our survey, we focus on hiring, so an example of a scenario might be the following. A hiring manager at a new sales company is reviewing 100 new job applications. They're then presented with a rule which the hiring manager will use to make the decision in a fair manner. For example, the fraction of applicants who receive job offers that are female should equal the fraction of applicants that are female. Similarly, the fraction of applicants who receive job offers that are male should equal the fraction of applicants that are male. Now, this particular rule corresponds to the fairness definition of demographic parity, but we used similar verbal descriptions to describe and create rules for each of the 4 fairness definitions that I described earlier. The survey contains 18 questions. 2 questions concerning participant evaluation of the scenario, 9 comprehension questions regarding the fairness rule, 2 self-report questions regarding participant understanding and use of the rule, 2 self-report questions of participant liking of and agreement with the rule, in other words, sentiment towards it, and finally 3 free response questions on comprehension and opinion of the rule. I like to draw your attention to the 9 comprehension questions because these are the ones that we actually use to create a measurement of understanding of participants regarding any given fairness rule. So this is how we get compute a comprehension score. Our cohort included 349 participants who were recruited through a web panel to approximate US distributions on 4 specific demographic categories, these being race, age, gender, and education, and these were matched to the 2017 census. So to go back to our first research question, can we develop a metric to measure lay understanding of machine learning fairness definitions? We believe we can, and we corroborate this using 2 different measures. Now, I stated earlier that we used, or rather our survey had a couple of self-report questions and a handful of free response questions. So the first way we corroborate the efficacy of our metric is one of these free response questions in which we simply ask participants, in your own words, explain the rule. We took these responses, these free responses, and coded them into one of 4 categories. These being correct responses, in other words, they correctly explained the rule, partially correct responses that they provided some correct explanation but maybe had a few mistakes here and there. Neither were irrelevant or off-topic responses to the question, and incorrect responses were obviously those that failed to explain the rule correctly or gave an incorrect explanation. On the y-axis, we see the comprehension score. So first we see the distribution of correct responses, partially correct responses, and then finally neither and incorrect responses. And you'll see here that those who were able to provide a correct explanation of the rule tended to do better according to our measurement. And this trend was statistically significant. In other words, those who can explain the rule, those who understand the rule, tend to perform better. Next, we asked, what did you use to answer the questions? We asked participants this question, and they responded with one of 3 options. The first being that they used the rule only, in other words, just the fairness definition that we provided. The second being that they used the rule plus some combination of their own personal notions of what a fair decision should look like in the scenario. Or finally, they simply used only their own personal notions of what a fair decision would look like here. And we find that participants who used only the rule tended to perform better according to our metric, which gives us some confidence that participants are being honest about their use of the rule and their application of the rule, and the fact that our metric actually measures comprehension of the rule. So in summary, we've confirmed using 2 different measures that our metric effectively measures comprehension of a given fairness definition. This being greater ability to explain the rule is associated with higher comprehension, and self-reported compliance with the rule is also associated with higher comprehension. Next, we look at the following research question: what factors play a role in comprehension? And we assessed this using a series of GLMs and then performed AIC model selection in order to figure out which one was the model of best fit. The model of best fit turned out to have two predictive factors. The first being, unsurprisingly, education. Specifically, those with a bachelor's degree and above tended to perform better according to our metric, exhibited greater understanding of the rule. The second factor was the fairness definition itself. Specifically, equal opportunity with a focus on false negative rates tended to be associated with lower comprehension scores. And we have some intuition of why this is the case. The image you see on the screen now is a screen capture of a portion of the survey that was given to participants who saw the false negative rate definition. Now, this definition focuses specifically on error rates. In other words, only qualified applicants who do not receive job offers, without really addressing all the other applicants who may or may not be receiving job offers. And this focus, because of this focus, we maintain the same focus within our survey. And this seemed to confuse participants to some degree, and this confusion was corroborated by the answers they gave to some of the free response questions, in which some participants explicitly stated that they found it confusing that over and over qualified applicants were being denied job offers. So we think that's what explains this particular phenomenon. So in summary, the two predictive factors for comprehension score were higher education level and the fairness definition itself. In our last research question, we looked at how comprehension score and sentiment are related. And we did this by asking two questions. First, we asked, to what extent do you agree with the following statement? I like the hiring rule. And this was assessed on a 5-point Likert scale, ranging from strongly disagree to strongly agree, with strongly disagree corresponding to participants who dislike the rule and strongly agree corresponding to participants who like the rule. We see here the participants who dislike the rule also tended to perform better according to our metric. In other words, those who understood the rule didn't like it, and this was a statistically significant correlation. We see a similar trend with the disagreement with the rule. When we ask the question, to what extent do you agree with the following statement, I agree with the hiring rule, assessed on the same 5-point Likert scale. This time, conveniently, strongly disagree corresponds to disagree, and strongly agree corresponds to agree. We find that those who disagree with the rule also tend to perform better on the rule. In other words, those who understand the rule, disagree with it. So what exactly does this mean? We find that negative sentiment, in other words, disliking or disagreement towards the rule, is associated with a higher comprehension score. We believe this suggests that people who understand the rule see its pitfalls. In other words, these rules are meant to try and maintain some semblance of fairness, but participants are able to see that there are many situations in which they would in fact not be doing so. Now recall that some of our data suggests that lower education level predicts lower comprehension. Specifically, those without a bachelor's degree tend to perform worse according to our metric. And this education category comprises 70% of the US population. So this creates a not so user-friendly environment, which actually incentivizes companies to obscure their algorithms so that users aren't really aware of what's going on in the background and are less able to actually identify bias if it in fact exists within those systems. So to summarize, we do in fact develop a metric that measures lay understanding machine learning fairness definitions. And we find using this metric that a non-expert audience can comprehend these definitions, but it depends on a number of factors, including higher education, as well as the definition itself. And in fact, comprehension is correlated with greater negative sentiment towards the rule. In other words, people who understand the rule simply don't like it or they disagree with it. Thanks for listening. Funding for this project was provided by the NSF and Google. I'm Debjani Saha. My contact information is on this slide. Should you have any further questions for me, on behalf of our group here at University of Maryland, thanks for listening and enjoy the rest of this conference.